My name is Ethan. I'm currently a PhD candidate in electrical engineering from Case Western Reserve University. And this is one piece of my PhD study, and I'm very glad here to have this opportunity to present this work. The topic is a non-contact variable wireless body sensor network for multiple vital signal detection. In this presentation, first I'm going to give a brief introduction of the background and the motivation of this research, followed by the system architecture. Then I'm going to talk about the sensor node design, include the non-contact electrode, the analog front end, and the wireless module. And then I will show some results and conclusion. Okay, so first, when we face a body sensor network, there are many important issues to address. The first component is that the sensor design, which means that what kind of data we want to detect. For example, the electrophysiological data, biochemical, acceleration, and temperature, and so forth. When we see the placement, it can be from the implantable to wearable. And also, when we consider the wireless communication, then the commonly used are really standard are Wi-Fi, UWB, Zigbee, and the Bluetooth. And also, when we consider the power and the energy, low power is always desirable. And the different kinds of power supply include the battery and some innovative energy source like the thermoelectric, vibration detected by piezoelectric, and also for the whole system, there are many commercial products for the whole system and also for the wireless module. For example, the iMode, iMode 2, and our work are focused on the Born one. Okay, so for the body sensor network, actually, we all know that it has a variety of applications. When we face the different kinds of application scenarios, the focus and the requirements are different. For example, when we want to use in clinic, then the high quality physiological signal are always desirable. And for example, if we want to use in sports, then the acceleration and also kind of different secondary parameters are required to detect. And the cost is a considered factor in sports monitoring. And for our research, we focus on the daily monitoring and the driving scenario. And we detect the ECG, EEG, and also eye activity, temperature, acceleration with components, combine them together. For our system, actually for daily monitoring, and the signal quality is moderate. It's not as high as the clinic one. And the cost is very low, and it's completely non-intrusive. And the power in this case is not a considered factor. So next, let's see the variable electric system. When we say the variable system, the skin contact is always a problem. In the current stage, there are different kinds of electrodes. There can be wet contact, and wet contact can always have high quality signal. And also another solution is the dry contact. For dry contact, the better contact is always desirable, which means that it's as good as possible. So there are different kinds of designs. For example, use a belt, here a belt, or a vest, a tight shirt, and also for EEG, it has this is the wax, and this is the string screw, and this is the needle. But all of them, even the dry contact, they can have high quality signals. And another solution is that we want to propose a completely non-contact, which means that it's not necessary to wear another coat or another vest, and it's not necessary even to use the belt. You can just place the sensor outside the clothes. So the motivation of our research is that we want to realize the transformation of healthcare from hospital-centered to human-centered, and we focus on the well-being management. So for daily monitoring, and for example, the elderly people and the chronic disease, and this figure shows some fact that the number of elderly people is dramatically rising over years. And also for driver assistance, for example, the detection of fatigue, stress, and emotion. And also the non-contact has an advantage to detect the burn skin. So next, let's see our system. This figure shows the overall system concept. There is a gateway node, and there are some different kinds of sensor nodes to detect different kinds of signals, for example, ECG, EEG, and eye blinking. And eye blinking is an important parameter for driving fatigue and driving assistance. Okay, so next let's see our sensors. This figure shows the sensor node, and this is the gateway node. There are totally 6 components for all of the systems. One is the communication board, and there are 2 layers of the sensing board. One is for the non-contact electrode, and the other board is for the temperature and acceleration. I will show that later. And the third one is the power board, and we use the battery and a power management IC. And the next is the fourth one is the antenna and the interface board and the layer 1 of the sensing board. And we can see that our non-contact electrode is as small as a cover. Okay, this is the diagram of the sensor node. As I just talked that there is a layer 1 for the non-contact detection, and it contains an analog front end and the electrode, which is just a solder on the surface, the solder mask. And there is a 3D accelerometer and goes to the amplifier filter and goes to the ADC. And using the SPI port goes to the iMotion module, which is the wireless module. And there's also a temperature module goes to the I2C. And the power supply gives power for both the sensing board and the wireless board. Okay, so I will describe the first board, the layer 1, here. For the non-contact electrode, I will go to the details of the design. So when we face this problem, the first is we want to see the basics of this cluster. So when you use electrode that is attached to the skin or even to the clothes or you wear a belt or a vest, there is a general skin electrode interface modeling, which means that each layer can model as a resistor and a capacitor. They are parallel to each other, and the signal goes through the path to the electrode, and each of the layers is serious to each other. So if there's no air and no clothes, which means that it's dry contact, then we can modeling the impedance like this. But if it is non-contact, which means that there is air layer, then the sensor impedance, the impedance for skin electrode interface have an additional item. This one, why it is a little bit challenging is that the coupling capacitance can be as small as 0.01 picofarad, and it's very small. It can cause very high sensor impedance. Okay, so from the analysis, we can see that it has the first challenging is that it calls for ultra high input impedance. That is almost needs to be higher than 10 to the 15 ohms to pick up the signal. And also, we all know that since this is very small, there is, and this one, and the C, they can cause a signal attenuation and signal distortion. So we need the ultra high input impedance. The second question is that for each amplifier, there is a belt current. We need to give it a path to let it go to the ground. But if we just use a common resistor, it cannot reach very high. And actually, this too is a trade-off, because if there is a high resistor, then input impedance will decrease immediately. So our solution is that we try belt connection, we use boost sweating, and we'll also try the real-to-real input stage. And this one can almost solve the problem. The next challenging is that it has high interference. In daily monitoring and also in the vehicle, so the power line and also the engine vibration can also cause high interference. So we need to have high CMR and SMR. For the offset, since the signal is very weak, if there is a little air distance, then the signal can be reduced directly. So we need a very high amplifier, so it is easy to saturation. The last but not least is that the motion artifact, and this is the most important thing in this design, because, for example, when a person is even just walk slow, then the motion artifact is very high, because this sensor impedance changes a lot. We can see from the cartoon. So it will cause the signal, cause a very high signal noise, and it can also cause the detection failure. So our solution is to use the capacitance normalization circuit, and it is to lower the sensitivity to the sensor impedance here. Okay. And also, a high performance notch is also used. Okay. So the next module is the communication module, and we use the MO2. For the CPU, it is PXA271, and for the radio, it is CC2420, and common. I guess this is common using body sensor network. It is using ZigBee and CMOS system coupled together, and also there's the antenna and the blind. And the radio frequency is 2.4 gigahertz. And this shows the sensor node performance. And this is for the EEG detection. And we can detect the secondary parameters, which is HR and HRV. We can see that we develop our algorithm to detect the peaks. And also, we can also detect respiration rate. And for eye activity, when we compare it to the video, we can see that this is our signal. And the T1 is the closing time, and T2 is the reopening time, and T3 is the opening duration. And this is our EEG signal, we compare with the tactile signal, we can see that our signal is very. So this is, I want to summarize my work. A framework for body sensor network has been developed, and the beta signal sensor node for human-centered healthcare is developed. And in the sensor node design, we solve the challenges of analog front-end design solutions, and also for the variable consideration, we use the completely net contact. And the first, and also this one is used in the implementation, and also we want to make it smaller and also stable. And thank you, and open for questions.